Okay, today we discuss about first order logic. What is knowledge engineering? Knowledge engineering is the process of constructing a knowledge base in first order logic. Um, in knowledge engineering, someone who investigates a particular domain, learns important concepts of that domain, and generates a formal representation of the objects is known as a knowledge engineer. An important area of artificial intelligence and expert systems is knowledge engineering, a domain in which an intelligent computer system tries to mimic human expert behavior. In the case of a digital circuit of some sort, such as a 1-bit full adder, as we will see later in an example in this lab, the knowledge engineer must first understand what the circuit does and the components involved. The circuit has some inputs, A, B, and carry in, some gates and or XOR, and corresponding outputs, sum and carry out. The understanding of the knowledge must then be formalized using first-order logic. This formal representation is used in automated reasoning systems to conclude or detect inconsistencies, to predict output values for any given set of inputs, or to detect faults in circuit design. Various scenarios are conducted to test the knowledge base and validate whether the system will behave as expected. Knowledge engineering also involves optimizing and simulating designs apart from circuit analysis. This ensures knowledge reusability in related domains and lessens manual expertise. The engineer attempts to represent the system's understanding using logic and rules and simulate human understanding to improve decision-making accuracy in real-time application. The knowledge engineering looks to bridge the gap between human expertise and machine reasoning, enabling artificial intelligence systems to decide and deal with changes while providing accurate outputs on highly complex problem domains. In the following, we will see the main steps of knowledge engineering process. Using these steps, we will develop a knowledge base that will allow us to reason about a digital circuit. In this case, we will use a 1-bit full adder. In figure 1, we have the 1-bit full adder. It has 3 inputs, as we can see, depicted as 1, 2, and 3. It has 2 outputs, S1 and S2. S1 is the sum bit, S2 is the carry out bit. Then we have 5 gates. We have 2 exclusive OR gates, we have 2 AND gates, and 1 OR gate. And this one entirely is the circuit, the C1. Now, in the knowledge engineering process, the first step is identifying the task. For the digit circuits, there are various reasoning tasks. At the highest level, we will examine the functionality of the circuit, and we will try to answer questions such as, does the circuit add properly, or what will the output of gate A2 be if all the inputs are high? At the second level, we will examine the circuit structure details, such as which gate is connected to the first input terminal, or does the circuit have feedback loops. Task identification is required as it defines the extent and direction of the knowledge engineering process. With a clarifying understanding of the functional and structural questions of a fully-fledged analysis follows. The functional tasks ask whether the circuit actually performs the intended operation properly. On the other hand, the structural tasks solve out the physical or logical placement of the elements, reduce to another type of design flow, optimize performance, or substantiate the behavior of the circuit. These questions assist in documenting the knowledge systematically for use in artificial intelligence training or simulation. This clarity facilitates efficient reasoning as well as smart troubleshooting within a circuit system. The second step, assemble the relevant knowledge. In the second step, we will assemble the relevant knowledge that is required for digital circuits. We have the following required knowledge for digital circuits. Logic circuits are made up of wires and gates. The signal flows through wires to the input terminal of the gate, and each gate produces the corresponding output, which flows further. In a logical circuit, four types of gates are used. We use gates of type AND, OR, exclusive OR, and NOT. All these gates have one output terminal and two input terminals, with the exception of the NOT gate, which, as we know, has only one input terminal. Uh, Gaining associated knowledge ensures that the knowledge base is formed on accurate and complete information. Understanding how the signals propagate, how individual gates operate, and how things are connected is required in logically modeling the circuit. The familiarity with timing, delay of signals, and logic levels, besides rudimentary gate operation, can model the representation even more accurately. Moreover, the identification of common subcircuits, such as multiplexers or half adders, can also be employed to simplify complex designs. Recording facts in a proper format suitable for first-order logic is also a part of this step, which makes inference work effectively and enables artificial intelligence systems to perform accurate reasoning over the digital circuit. The third step is deciding on the vocabulary. Here we have to select the functions, predicates, and constants to represent the circuits, terminals, signals, and gates. Firstly, we have to distinguish the gates from each other and from other objects. Each gate is represented as an object named by a constant, such as gate x1. Basically, we have the gate with the name x1. The functionality of each gate is determined by its type, which is taken as constants such as AND, OR, exclusive or not. Circuits will be identified by a predicate, circuit C1. Okay, so we have circuit with the name C1. For the terminal, we will use the predicate terminal X, where X is the name of the terminal. For the gate input, we will use the function in1x1. So basically, we specify the input signal 1 to the element x1, to the gate x1. And for the output terminal, we will use out1 x1, basically the first output of the terminal x1. The functionality Cij is used to denote the circuit Gc as I inputs and J outputs. The connectivity between gates can be represented by the predicate connect out 1 x1 in 1 x1. So basically here we specify that there is a connection between the first output of the gate x1 to the first input of the gate x1. X1, okay, so basically here are two gates, okay, so x1 is used as a placeholder. We can also use a unary predicate on T, which is true if the signal at the terminal is on. This conversion converts physical and logical structures of a circuit into formalized expressions that the reasoning system is able to read. The application of constants, predicates, and functions enables us to define advanced relationships exactly. For instance, by using functions such as in and out to indicate inputs and outputs, signal flow can be graphically represented. By representing the behavior, structure, and connectivity in logical forms, the system can infer circuit behavior for a variety of conditions. In addition, formalization of this kind facilitates automatic verification, fault analysis, and performance assessment. Logical functions ensure that the knowledge base can be scaled and extended in such a manner as to include larger and more complicated digital designs and circuits in an economical fashion. Step 4. Encode general knowledge about the domain. To encode the general knowledge about the logic circuit, we need to define rules. And here we have some examples of rules that we can define. If two terminals are connected, then they have the same input signal, okay? So we have here, for any T1, T2, where T1 and T2 are terminals, and there is a connection between terminal T1 to terminal T2, this implies that signal T1 equals signal T2. Okay, so we have the same signal between terminal T1 and terminal T2. Next rule, signal at every terminal we have either value 0 or 1. Okay, we cannot have other signals, other values for the signals. So for any t where t is a terminal, signal of the terminal t is either 1 or 0. connect predicates are commutative. Okay, so we have a connection from T1 to T2, but also from terminal T2 to terminal T1. Okay, so for any T1 T2, there is a connection between in the both ways. Now, how can we represent types of gate? Okay, uh, for any uh, for any given gate G, okay, um, and R equals to type of G, so basically R is the type of the gate. This one implies that R can be a gate of type or a gate of type AND, or a gate of type exclusive or a gate of type NOT. Now, let's see how can we depict the output of the gate OR. The output of the OR gate is 1 if and only if any of its input is 1. So here we have, for any G, where G is a gate and type of G equals to OR, this implies that signal out 1G, basically the first output of G, of the gate, is 1 if exists a signal N, signal in NG equals 1. So basically there is a signal that enters into the gate that is 1, okay? So the output of the gate is 1 if one of the signals, of the input signals, is 1. The output of a NOT gate is the invert of its input, okay? So basically a NOT gate changes the value of the input from 0 to 1 and from 1 to 0. So for any gate G, where the type of the gate G is not, the signal in 1G, so basically the first input into the gate, the value of the first input into the gate is different from the output signal, okay? So basically the input is different from the output. All the gates in the above circuit have 2 inputs and 1 output, with the exception, as we said earlier, of the NOT gate. So for any given gate G, where the type of the gate is NOT, we have the RET, this function. We discussed a bit earlier about functionality. Functionality specifies the number of inputs and outputs for a gate. Okay, so here we specify that for the gate G, we have 1 input and 1 output, okay, because the gate NOT receives 1 input and has 1 output. Next, for any given gate G, okay, where R is the type of the gate, and R, the type of the gate, is either AND or exclusive OR, the functionality has the value G to 1. It means that this type of gates have 2 inputs and 1 output. And lastly, all the gates are logical circuits. Okay, so for any given gate G, G is also a circuit. Now, step 5. Okay, decode a description of the problem instance. Now, the circuit and its gate components are categorized. This step involves writing simple atomic sentences of instances of concepts, which is known as ontology. For the given circuit C1, since in the circuit we have 2 exclusive OR gates, 2 AND gates, and 1 OR gate, the atomic sentences for these gates will be like this. So we have the exclusive OR gates. But first, let's look at this schema. Okay, so we have 5 gates. 2 are exclusive OR gates, 2 are AND gates, and 1 is OR gate. Okay, so for the exclusive OR gates are x1, x2 respectively. AND gates are a1, a2 respectively, and OR gate is o1 respectively. So exclusive OR gates, we have type x1 equals exclusive OR. So first, the gate x1 is exclusive OR. Next, type x2 equals exclusive OR, so basically the gate x2 is exclusive OR type. And the same for the AND and OR gates. And at step 6, here we can pose queries to the inference procedure and get answers. We will find all the possible sets of values for all the terminals of the other circuit. The query will be what should be the combination of inputs that would generate the first output of circuit C1 to be 0 and the second output to be 1. And the query will look like this. There is I1, I2, I3. These are input values. Signal in 1C1 equals I1. What does it mean? It means that the first input of the circuit C1 has the value I1. And now we have signal in to C1 equals I2. Here we say that the second input into the circuit C1 has the value I2. And the same, and the third input of the circuit has the value I3. And we also have to specify the values for the output of the circuit. Signal out 1C1 equals 0. It means that the first output of the circuit has the value 0. And signal out to C1 equals 1. It means that the second output of the circuit needs to have the value 1. In this way, we can infer the values of the inputs. Through questioning, we can make helpful inferences, such as identifying some condition inputs that lead to desired outputs. For a one-bit full adder, it is necessary to pose questions regarding the combination of the inputs A, B, and carry in that lead to a given sum and carry out for testing and verification. The inference engine checks via logical rules and relations already programmed to give accurate responses. Backward reasoning is also possible where the outputs are given and the inputs need to be deduced. Such a query is greatly helpful in debugging circuits, in optimization, constructing systems with predetermined logical outputs. And we have 3 tasks that you can think about them, and when you have time you can present them. Exercise 1, identifying vocabulary. Here the objective is to define the logical vocabulary for a basic digital circuit. And the task is to list at least 5 constants, 5 predicates, and 2 functions based on the full adder circuit. And some examples include constants could include the gates name x1, a1, 01, o1, sorry. Predicates might include the gate x, type x equals n. Functions could be in1x, where in is a function that depicts the input signal. The second exercise is to translate circuit to first order logic. The goal is to express part of the circuit behavior in first order logic, to write the first order logical formulas for the behavior of the exclusive OR gate. Remember that the output of the exclusive OR gate is 1 if and only if its own inputs are different. And also to specify the formula for the behavior of the AND gate. The output of an AND gate will be 0 if and only if any of its inputs is 0. Going back to the example, remember that we had an example here for the output of the OR gate. OR gate is 1 if and only if any of its input is 1. For the AND, the output of the AND gate is 1 when all the input signals are 1, okay, as a help for you. And the last exercise, input-output querying. The goal is to query the system to find logical states. The question is which combination of inputs A, B, and carry in leads to sum equals 1 and carry out equals 0. And again, if you have here an example at step 6, here was the example for querying the system when the signal, the out signal for the first output is 0 and the output for the second, the out signal for the second output is 1. It's just a small difference. Thank you very much.